So for homework, you guys had two word problems that had to do with exponential functions. The first one had to do with our interest problems that we were going over yesterday. And then the second one had to deal with half-life. Both similar procedures, right? Just different equations. So the first one, you had to come up with the equation yourself. Now you're going to use the formula I gave you yesterday for interest, right? And as a reminder, okay, that was A equals P times e to the RT, where A is what we're looking for, the amount in the account. P is your principal, what you start with. R is the rate, and T is how long it's in there. So for the first problem, we had on the day of your cousin's birth, your family creates a savings account and deposits $25,000 into it. That's a pretty good bank account. Wish my family did that. The account pays 8% interest. How much money will be in the account if it is compounded continuously? Okay, so that tells us this equation. If they wait until their 21st birthday, right? So that money's sitting there until you're old enough to use it, maybe for whatever house or something. All right. So we want to find out how much is in there. So just to organize things, right? We have our three values that we're plugging in. The principal was 25,000. The rate is 8%. Again, remember you have to change that to a decimal, so that would be 0.08%. If you typed in 8, you get a very large number. And the time, well, if you're going from birth to your 21st birthday, okay, that's going to be in there for 21 years, which is quite a lot for a bank account. Okay, obviously, you know, the longer you have it, it exponentially grows with respect to how long it's in there. All right, so we're going to just plug in our values. We have 25,000 times e to the 0.08 times 21. Okay, so again, depending on what calculation tool you're using, if you have an actual calculator, you can just type everything in at once. So we have 25,000, times e, and then even up here, okay, in this exponent, I could just type 0.08 times 21. Let me see if I can. There you go. That's a little better. All right. Again, depending on what you're using, you might have to calculate what is 0.08 times 21. All right, but here everything's where it's supposed to be. So that is quite a bit of money. So after 21 years, you're going to have $134,138 and we'll say 90 cents. All right. So after 21 years, you got well over 100 grand. All right, so there we have our first problem. All right. So just, you know, a word of advice. I rounded to the second decimal place, or the hundredths, because we're talking about money, right? So money, if we're talking about cents, you have two decimal places. It doesn't go past that. So these wouldn't matter. So you would round that 9 up, which bumps up the 8. Okay, any questions about that first one? That was pretty straightforward. All right, then for the second one, we had a half-life problem. Okay, so here we have radium. Radium's half-life is 1,620 years. All right, so again, if you had 1 gram of radium in 1,600 years, that would be half a gram, right? And so on and so forth. The quantity of radium present after T years is given by this equation. How much radium is left after 1,000 years? Okay, so yeah, and here I just told you that it looked a little funny. So this was, I just let you know that this part was the exponent. So that's even a little more straightforward. All you're doing is plugging in T equals 1,000. Right? So the equation we have is 16 times 1/2 to the 1,000 over 1620. Now, I'm going to calculate this first. I'm not sure if I mentioned this yesterday, but whatever you reduce that exponent to, okay, this number that you get is the number of half-lives it goes through, right? So in 1,000 years, we don't make it through a full half-life, right? And that kind of makes sense, right? It's a little over half of a half-life. And the problem we saw yesterday when we were looking at a larger amount, we looked at 100,000 years, right? That was 4 half-lives. So that means you took half of whatever your starting amount was 4 different times. Okay, so doing this, we have 16 times 1/2 to the, actually up here in this exponent, I'm just going to type in 1,000 divided by 1620. Oops. All right, so after 1,000 years, we still have about 10.43 grams of radium left. Right? And like I said, it's not a full half-life. Okay, so 10 obviously isn't half of 16 yet, right? If I went through one full half-life, I'd only have 8 grams left, right? And then if I went through another half-life, then I'd have 4. And then if I went through another half-life, I'd have 2, right? And we keep dividing by 2, right? And that's where that base of 1/2 comes in, right? From the half-life. All right, any questions about that? Okay, so today is going to be a bit of a discovery lesson. So we're going to go back to a topic we haven't talked about in a minute. And then we're going to tie it in with our exponentials. But first, let's talk about inverse functions. So what do we remember about the relationship between the original function and its inverse? What are some properties between those two functions that they share? Or what are some things? How do you get from a regular to an inverse?
I do remember that that like the inverse and the original, like if you solve it, they both equal x.
Okay, so if you plugged, well, so if we have an original function x, and if we have the inverse, right, to the negative first, right, so if you plugged one into the other, right, we just get x. This told us something, right? Specifically, it told us about the graphs. All right, so what do we remember about the graphs of two inverse functions? Do we remember what they are? Let me give you a quick. All right, so there we have our original function and we have its inverse. What do we remember about these two graphs? What happens? How can I get one from the other? There's two things I'm looking for here. I know it's been a while.
On the graph, they're like reflections of each other.
Reflections? Do we remember what the line they're reflected over is? Is it a reflection over the x-axis or the y-axis? It doesn't look like that, right? It's not a vertical or horizontal reflection. What is our reflection line for inverse functions?
Over x.
Over x. All right, over the line y equals x. Right. So if you had that invisible reflection line, it would pass right through the middle. Okay, good. So another part of that, okay, is our domain and our range swap. Okay, right? All of the x values of my original function become the y values of my inverse. And all the y values of my original become the x values of my inverse, right? Okay, so good. So now that we have a base there, let's use that. There we go. So let's graph, yeah, let's pick a nice one. Let's do 2 to the x. All right, so here we have the function 2 to the x. All right, and I picked this one because we can get some nice clean numbers in here. Real quick, I'll show you e to the x. It's going to be kind of similar. All right, so let me get rid of that one. So there's e to the x. But since e is not a natural whole number, the values we get here aren't going to be whole numbers, right? If you plug in 1, you're not going to get 2. Right, so for now, we're going to take a look at this nice one here because we got some nice numbers that we can work with. So let's plot the reflection line. That's not what I want to do. Okay, so here's our reflection line. Let's make it red. Let's make it dotted. Yeah, that looks good. All right, so there's our reflection line. Let me make this big so. All right, so let's start looking at this and start plotting some points. So a good point we can start with is the y-intercept, right? Here we have 0, 1. So to reflect that, I'm going to switch those values. So for the reflection, I'm going to have 1, 0. So I can put a point here. Continuing up this way, we'll plot a few. So here I have the point 1, 2, right? If I plug in 1 into my function, I get 2. 2 to the first power is 1. So the inverse of that, 1, 2, is going to be 2, 1. All right, so my next point is going to be here. 3 is a little weird, but I know at 4, over here at 2 on my original function, when I plug 2 in, well, 2 squared is 4. So up here, I have the point 2, 4. Reflecting that, that's going to give us 4, 2. All right, so we can kind of see how this reflection is working. All right, and then if I plug in 3, I get 3, 8. So I would have 8, 3. Now this is kind of starting to look like maybe a square root function, but something happens when we go to the left. If I plug in -1, okay, 2 to the -1 gives me a fraction 1/2. So here my point is -1, 1/2, which means my reflection is going to be 1/2 -1. All right, so it's not going to be perfect, but I'll put a point somewhere in between here. Yeah, that looks good. When I plug in -2, okay, that gives me a fraction 1/2 squared, or 1/4. So at 1/4, I'm going to be down at -2. Right. So let's see if that matches up. So here I have a nice tool. I can actually click this and then here, and look at there. There is our reflection line. I'm going to make that a different color. Let's make that blue. I don't think that changed anything. Oh, I did the wrong thing. Okay, so here we have an interesting thing going on. All right, if I move this around or if I zoom out a little bit, okay, it kind of looks like a hyperbola, right, when we were dealing with radicals, but not quite because they're two separate functions. Let me get rid of these. We don't need these. Okay. It behaves opposite, right? So here we grow exponentially. Here we're growing, but it's not really that fast, right? It kind of tapers off. Here, our range is all positive numbers, right? Anything greater than 0. So for the inverse, that means our domain has to be greater than 0. If I keep following this down, I'm never going to cross on the other side of that y-axis. What we have here is the inverse function of our exponential. What that is what we're going to learn about in depth next week. Something called logarithms. There's a lot we can do with logarithms. They're used in real life, a lot in science, okay, you know, kind of obviously. We use logarithms when we are talking about sound. Okay, I'm not sure if you guys talked about things like decibels in any of your science classes, all right, but sound is measured in decibels, right? The louder it is, the more decibels it is. Decibels are calculated with logarithms. Earthquakes, the Richter scale, right? Things like that, the magnitudes are calculated with logarithms. Okay, it's the inverse of our exponential. It still grows. So here, the domain of our logarithms, like we just found, okay, x has to be greater than 0. So when we're dealing with logarithms, you can't take the logarithm of a negative number. It doesn't work. It doesn't make sense. The range is going to be all real numbers. Okay, going back and looking at that graph, right? Obviously, I go down for infinity, right? I can keep going down, and it's, I mean, there it stops just because this is like, you know, 0.0000 whatever, a million zeros and then a 1, so it just stops the graph. But if I zoomed in, nope, that's zooming out. Why isn't the zoom working? Oh, that's why. Hold on, let me move that. Oh, it actually disappears there. But it'll be really close to that x-axis. There's a line there, trust me. All right. And then going all the way back up, okay, it doesn't grow as fast. Oh, I went really far down. Too far down. Okay, it's going to keep growing. It's just not a really fast rate. Okay, like I said, here it kind of looks like, oh, that was weird. Kind of looks like a square root function, but it's slowly growing, right? You'd have to plug in large numbers to get above a certain line, right? So next week, we're going to actually learn about the logarithmic logarithmic function. Okay, the way that looks like is run out of room here. Okay, you might have seen it on your calculators. It actually says log, right? So you have y equals log of x. Like our exponential functions, we had bases, all right? We have bases for logarithms. So again, next week we'll take a deeper look into that and the relationship and how logarithms behave. All right, any questions?